Relationships involving delta H. So if we multiply the reaction by a factor, say we take this simple equation and we multiply everything by 2, we double it. Then we have to double the heat, right, the enthalpy. Because if we're using twice as much reactant, we're going to get twice as much energy. If we reverse the reaction, if we turn it around, we don't talk about this a lot in general chemistry, but most chemical reactions are actually reversible. Sometimes you have to convince the reaction to go in the other direction, but most of them you can make go either way. So if we take, instead of combining carbon and oxygen to form carbon dioxide, if we take carbon dioxide and decompose it into carbon and oxygen, it's just going the other direction. Delta H is going to be the same, but the sign will be different. So if you have to put so much energy in, well, let me take that back. Let's stick with the example here. If we get this much energy out when we do this forward reaction, then we have to put that much energy in to get the reaction to go the other way. Everybody okay with that? We're just turning it around. It's like, if you, what could you buy and resell for the same amount? Oh, you could return something. So you bought a pair of jeans at Target for $25, right? You gave them $25. That was a negative in your bank account, and you got the pair of pants. And then you decide that you don't really like them after all, or your boyfriend said, mm-mm. And so you take them back to Target, and you give them the pants, and what do they give you? They give you the $25 back. Okay? So this is buying and returning. Okay?
What if there was like a 3 in front of a C?
If this was 3 and 2, then when you doubled it, it would be 6 and 4. And reversing, here we're just talking about reversing without multiplying by numbers. Another interesting thing, because delta H is a state reaction, if we can, a state function, good grief, if we have a reaction that can be expressed as a series of steps, then delta H for the overall reaction is just the sum of the heats for each of the individual steps. So this is a little bit like, if we're talking about a change in elevation, and say you're going up to Grant Grove, and let's just say it's 7,000 feet for round figures' sake. You leave Fresno, you go up there. The change in elevation, 7,000 feet. What if you stop for lunch at Squaw Valley? You went up to Squaw Valley, which I'm thinking is like 2,000 feet or so, I don't know, making up numbers. You stopped at 2,000, and then after lunch, you continued up to the park another 5,000. Would your change in elevation be the same? Yes. Yes, it would. Right? Even though you stopped in the middle. You can add those together. It doesn't matter how you went. If you took a helicopter and flew way up to 10,000 feet and then came down and landed in the park, your change in elevation from Fresno to the park is still the same. It doesn't matter how you got there. Does that make sense? So this is a very useful thing that allows us to calculate heats of reaction for reactions that are impossible to measure the heat of reaction for. I mean, some of them we can do in a calorimeter and measure them. Others we can't. So let me look at this a minute here. So if we have A plus B, A plus 2B, and our ultimate goal here is to go to 2D. I think I'm supposed to be writing something here, I'm pretty sure. So if we have, which maybe this was off to the side for a reason, actually, now that I think about it. A plus 2b going to 2d. That's our overall reaction that we're interested in. Well, if we took, I'll do this on the other side. If we had a plus b, a plus 2b, and that went to c, but then c went to 2d, what would we get if we added those two equations together? We get a plus 2b plus c on the left, right? Going to c plus 2d on the right. And what happens to the c's? They go away, right? And if we think about this chemically, if A and two of the B's react to form C, and then C reacts to form this, is there any C left? No, there isn't. So these two equations can be added up to give this overall equation that we're interested in. If these are two reactions that we can measure delta H for, then all we have to do is add the delta H's, and we can calculate delta H for this overall reaction that was impossible to measure. So delta H3, which is from here to here, is equal to this plus that. This is like taking the helicopter. You went way above where you needed to go, and then you came back down. Does that make sense conceptually? So let's do an example. Find delta H of reaction for this equation. N2O plus NO2 goes to 3NO. I like this molecule. It looks like no, right? Because all caps is yelling. So that's yelling at us. No, which is what you say to children. And we've got these pieces that we can work with. These are things where the delta H has been measured and recorded, and we were able to find these. So what we have to do is figure out how we can combine these three equations to get this one. Doesn't that sound like fun? No, it doesn't. What are you, a crazy person? Why, yes, I am. How do we even start something like this? Well, let's start with putting a reactant on the reactant side. Let's start with the top equation. This NO is a product, isn't it? So we probably want this to be on the other side. We just learned that we can reverse the reaction if we change the sign of delta H. And doing problems like this often requires some trial and error. Well, it helps to pull out a pen first. 2NO. In this example, all the states are gases. Do you see that? All the states are gases. So we really don't need to worry about the states, so I'm not going to write them down when I'm messing around. Other reactions, it does matter, but this one it doesn't. So I'm writing that first one. I left off the 2. I'm writing it backwards. I'm writing the products as reactants, plus O2. Did I do that right? 2NO2 goes to 2NO plus O2. And then what I have to do to delta H is change the sign, because I went the opposite way. So delta H is plus 113.1 kilojoules. Well, let's look at the second equation. There's N2 and O2, and here's NO. Now, if I add this equation to this one, because I don't want this O2 over here. I don't have any O2. I want to get rid of that. So if I take this one and add it on, maybe I can get those O2s to go away. So I'm just going to write this one down the same. N2 plus O2 hang on. I'm going to try to keep my arrows lined up because it makes it easier to see what's going on. N2 plus O2 goes to 2NO. And there I didn't do anything to the equation, so I'll just put in delta H is the same, plus 182.6 kilojoules. Now I could say that that guy and that guy are going to go away, right? Because the O2 that gets made in this reaction gets used up in this reaction. And so it's not around anymore. I'm getting closer, but I've got NO2 on the left. I do want some NO2 on the left. I also need some N2O over there. So I'm going to have to use this guy as well because that's got the N2O. So I'm going to put 2 N2O. And that's going to go to 2N2 plus O2. And the delta H for that one is minus 163.2. Well, this guy also has O2, and so now I'm looking at this thinking, you know, I shouldn't have canceled those out yet because, I mean, we were going in that direction, but we weren't really done enough yet. So let's just draw those guys back. So how close are we here? We've got NO2, we do need that. We've got N2O, we need that. We've got this N2 and O2, and we don't want either of those on the left side. Do you see what I'm doing? So I need to get rid of both of those. Over here, I've got two N2s and an O2, and there's an O2. Well, I've got two of these. If I multiplied this whole equation by 2, let's try that. So I'm gonna use a different color here. I'm going to put a 2 in front of the N and a 2 in front of the O, and this is going to become a 4. If I double the amount of the reaction, what do I have to do to delta H? I have to double it as well. So then doubling this, I multiply this by 2. And now let's look at what's going on. Now I've got the 2N2, we'll cancel the 2N2 over there, and I've got two O2s. There's one here and one there. So I have a total of 2 of them on the right side and 2 of them on the left side, and so those are going to go away. Now I only have reactants and products that I actually want, right? The only substance left on the right side of the arrow is NO, and that's what I've got here. And on the left, I've got NO2, this guy, and N2O. So now I'm going to add these together. So I did not leave enough space, but we'll manage somehow. So on the left, I have 2 N2O plus 2 NO2. Like I said, I can't see what I'm doing. And on the right, how many NOs do I have?
6.
I've got 6. I've got 4 here and 2 there. So that's 6 NOs. Now that looks like hoe. It's really close to this, isn't it? How's it different? It's multiplied by 2. Well, let's go ahead and add up our delta H's. So I've got plus 113.1, and then I've got 182.6 times 2, and then I'm going to subtract 163.2. And I end up with it's a positive number, 315.1 kilojoules. delta H is for the reaction as written. I can't take this delta H and write it for this reaction. What do I have to do? I have to divide by 2. I'll divide by 2, and delta H equals 157.6 kilojoules. Any questions? Yes, the first delta H is negative. The reason I wrote it positive here is because I wrote the reaction backwards. Yep. I wrote this one backwards, and this one I multiplied by 2, and so that's why I multiplied by 2 over here. And that's why we talked about if you do something to the reaction, this is what you have to do to delta H. Any other questions?